There we go. That's... I hope that was a person who says I don't care about my students at all. I hope that was a joke, actually. But anyway, so let me take this presentation off. And we'll start sharing. Oh, thanks, Jeff. Okay. So, okay. So tonight we are going back to optimization. There was this. There we go. Okay, so as you recall, what we were doing last week, for about the last half of class, we were covering optimization problems. And as I made the point, optimization is really, what you're really doing is you're taking a word problem and trying to create the correct objective function and feasible domain. We know how to find the maximum and minimum of minimum of a continuous function on a closed and bounded interval. And when the interval is not closed and bounded, at least we know how to characterize the critical numbers and say whether they are maxima and minima. And we'll learn a couple of other techniques for determining when absolute absolute maxes and mins exist when the interval is not closed and bounded. But what I found is that the main problem in solving, in the main difficulty in solving these problems is really setting up the objective function, performing all the steps. So I'm going to do a little bit more of that. And then we have a couple of problems toward the end where, I just, I'll just set up the objective function or maybe ask you to set up the objective function. So anyway, I will now turn off the video because, of course, you guys don't need to see me being unsafe. So let's see. There we go. Okay. So the last of these that we did we had done this problem, a rectangle inscribed inside a parabola. This was really meant to demonstrate two things. First of all, that you really need to sometimes reach back into your knowledge of geometry in order to solve these problems, because a lot of them do have kind of a geometric flavor to them. The other is that this problem was intended, I don't think I made the point at the time, but it was intended to demonstrate the use of a symbolic constant. One of the things I was reminded of today when somebody was asking me during office hours is that a lot of students don't fully grasp the difference between a variable and a symbolic constant. So if you notice, the parabola that was given in this problem was y equals r minus x squared, where so it's got the two letters in it. It's got an r and it's got an x on the right side of the equals sign, but they represent different things. R is a symbolic constant and x is a variable. What that means is that R represents a value that's simply not known, but that is considered to be fixed. It's considered to be unchanging. The x, on the other hand, represents a value that can change over some interval of numbers. So you can sort of think of this problem like as if I had said something like y equals 12 minus x squared. I didn't. I said r because I could just as well have said r equals 22 minus x squared, and it would be basically the same problem with a different number. You can't differentiate this y with respect to r because r is just a constant. X is the thing that's a variable and it actually changes and gets its own axis. The point here is that if you noticed, the only thing we were really able to say about this problem when we actually solved it was that the dimensions of the rectangle, we could specify them in terms of R, but we couldn't say what they actually were. There is a problem on Sapling that works kind of like this. It involves constructing an open top box. I'm going to do the open top box problem with a number, but it's sort of going to be up to you to combine this technique of using a symbolic constant and the technique for solving the open top box problem, which I'll do with a specific number, and you can kind of combine those two and come up with a solution that Sapling is looking for there. Okay, so let's see which problem I want to do first. Actually, I think I do want to do the open top box problem first. Okay. Okay, so let's find the volume of the largest open top box that can be made from a piece of cardboard 24 inches square by cutting equal squares from the corners and turning up the sides. So let's draw what this looks like. In other words, suppose that someone has just given you this piece of cardboard. So this is a square piece of cardboard. It's 24 by 24. And what you're going to do is you're going to cut corners out of it, and they're all going to be the same size corner. So I'm going to cut this corner, and this corner, and this corner, and this corner outside the box, out of the box. And they're all going to be equal size corners. And they're all squares. So this is an x by x square. This is an x by x square. They're all x by x squares. And then what we're going to do is we're going to construct the box by sort of flipping up. Right way to draw it. Sorry, it takes me some concentration to draw these 3D figures. There we go. So we're gonna draw this box. Yep, that's how you do that. That's right. I'll get good at that one of these days. Oh, there's one. Okay, so the idea is that we're going to flip up the corner. We're going to flip up these tabs. In other words, this region here, that region there becomes a tab and it gets flipped up. And since its length is x, that becomes the height of the box. So the idea is that we want to choose the value of x that that produces the maximum volume box. So let's do that. Okay, so first of all, you want to do is answer the question, what quantity is to be optimized? And actually, this is a good example. This is a good place where I can do sort of a poll and say A, length x, or B, volume of the box. All right. So since I don't know how to use the poll feature on here, let's say, just post your comments and say either A or B. Okay, good. It looks like the overwhelming choice is B, which, by the way, doesn't make it right. It just happens to be correct because correctness is itself not a democracy. But that is correct. It's the volume of the box that we're trying to optimize. We're trying to find the value of x that optimizes that quantity. So, all right, so 2. Let's write volume as a function of another variable. What we can do is we can describe the volume of this box as and describe the volume of the box in terms of x, sort of this way. If you look at the this different color, this region that I'm drawing in purple is going to become the bottom of the box. So that's really going to be this bottom here. And if you look at what size it's going to be, I'm going to take 2 bytes of size x out of the length of the cardboard. So this is going to be 24 minus 2x. And this is also going to be 24 minus 2x. So that's going to be the dimensions of the bottom of the box. We can write those in here. So this is going to be a box that has volume 24 minus 2x. We're going to call that length. 24 minus 2x, which is width, and x, which is the height. We all know that volume of a rectangular solid is length by width by height. So that gives us the formula for the volume of the box. And notice that this is very neatly just going to be a function of x. So v of x is going to equal 24 times 24 is 576. These come out to 96x. Right, yeah. And then plus 4x squared, and that's all times x, which gives us 4x cubed minus 96x squared plus 576x. So that's the objective function in this case, is this. And recall that we need to find the domain. And again, of course, this function it's a polynomial function. It's defined every place mathematically, but what we're interested in is not the mathematical domain, but its feasible domain, values of x that actually make any sense. So what are the bounds on x? What's the lowest possible value of x that I can choose? Ah, there we go. That gives the complete answer, doesn't it? So we can't choose x any smaller than 0. We could choose x as 0, but then we just get a flat box of no volume. We also can't choose any x any larger than 12 because we're going to take 2 bytes of size x, and if we choose the number larger than 12, we eat up the entire box. So the domain is, in fact, 0 to 12. Good. Okay. So there's our domain. And okay, so what we want to do is optimize v of x equals 4x cubed minus 96x squared plus 576x on the domain on the interval 0 to 12. So v prime of x is going to equal 12x squared. This comes out to 192x plus 576. So this is going to be a little easier to deal with if I factor it, because the idea is I want to set v prime to 0. So this becomes 12x squared minus 16x plus 48. I think that's correct. And in factored form, which is going to make it easier, that is x minus 12, x minus 4. There we go. So the zeros of this function, v prime of x equals 0, implies that x equals 4 or 12. Note that we were already going to check 12 anyway because it was an endpoint, but it turns out that that it's also a place where the derivative is 0. So now what we want to do is substitute the endpoints 0 and 12 and the critical number 4 into the original function. V of 0, I mean, recall that what we're doing here is we're doing this. Since x is going to become the height of the box, if I choose x equals 0, I'm going to get a box of no height, and it's going to have a volume of 0. You could also get that just by substituting in 0, but geometrically it should be clear that's going to be 0. V of 12, we could actually substitute in 12 and calculate 4 times 12 cubed minus 96 times 12 squared, etc. But again, it's really the same argument that if I choose x equals 12, then recall this was 24, this comes in by 12, this comes in by 12, and we have no material left. So we'd end up with a box that has 0. You could do that just by plugging it in, but geometrically, once again, you can see that's 0. If I put in 4, then I get 4 times 4 cubed minus 96 times 4 squared plus 576 times 4. That actually comes out to 1024, which is obviously greater than 0. So this is the largest volume box that we can build, and we do it when x equals 4. So recalling that the dimensions of the box are 24 minus 2x, 24 minus 2x by x, that comes out to a box that is 24 minus 2x is going to be 16. So this is a 16 by 16 by 4 box. So what you want to do is set x equal to 4 to build a 16 by 16 by 4 box. And these are the dimensions of the box that has the largest area that can be built in this way. Okay. So any questions about that? Okay. Let's see. Which one of these should I do? So all of the problems we've done up to this point involve optimization on a closed interval. Recall that the interval here was 0, 12. I think in the farmer problem, we had an interval of 0 to 60, and in the rectangle inside a parabola problem, the interval was 0 to the square root of r. Not all optimization problems necessarily involve a closed interval, which means you have to have a couple of different ways of dealing with intervals that are not closed. So I'm going to demonstrate one of these problems. And that's the one I was going to do for now. Okay, so let's design a cylindrical can of volume 900 cubic centimeters so that it uses the least amount of metal. I know you all know what a can looks like, but just to be clear what we're describing, the can looks like this and actually includes its top and bottom. That's worth saying because technically the shape that we call a cylinder only includes the sides of the cylinder, not the top and bottom. So a can is actually a slightly different shape than a cylinder when you're considering its surface, because it also includes its top and bottom. So the question is, what are the dimensions of the can that uses the least amount of metal and still holds 900 cubic centimeters of tuna. So the dimensions of a cylinder can be described by its radius and its height. So it's okay. Corn, is that better? So okay, that's good. One of the things that I've discovered actually, and I've discovered in this time when we're all seeking out non-perishable foods, is that actually canned chicken is surprisingly good. I've got quite a supply of that here at home. So anyway, the volume. So a couple of things about a cylinder. We really need, in order to use the least amount of metal, what we're saying is that we want the surface area to be as small as possible. So the quantity to be optimized is surface area. So we're going to need to be able to write the surface area in terms of one variable. So first of all, look at the top. Actually, let's do the sides of the can. The circumference of the circle that forms the base is 2 pi r. So if you sort of imagine yourself like kind of unrolling this can to form kind of a rectangle, what's going to happen when I unroll it is one side of the rectangle is going to be 2 pi r and the other side is going to be h. So the sides of the can are going to be 2 pi r h, and then plus the top of the can. Top of the can is just the area of a circle of radius r, so that's pi r squared, and then the same for the bottom of the can. So this is the top, this is the bottom, and this is the sides. So okay, so there's a description of the surface area of the can, the amount of metal we need. What is the problem at this point that prevents me from using this? Correct. Has two variables. So what we want to do is get rid of this one variable. The thing to observe here is that the volume of the can is equal to the area of its base, that's circle pi r squared, times its height. So, and we also know in the problem statement that that's 900. So that means that h, equating this with this, gives us h equals 900 over pi r squared. So I can replace that term. This becomes 2 pi r times 900 over pi r squared. And then I add those two circles together and get 2 pi r squared. So here, that cancels. Oops. 2 pi, the pi's cancel. One factor of r cancels, and I get 1800 over r plus 2 pi r squared. And that's the objective function, surface as a function of radius. So this is the objective function that we're now going to optimize. So basically what this is going to tell us is the optimal rate. When we finish the problem, this is going to tell us the optimal radius for this can. And since we already know the relationship between the height and the radius, we'll just be able to plug that radius in to this formula and we'll be able to get the height back. So, okay. Now, we need to figure out what the domain is. Okay, so what's the smallest that I can set the radius to? So 0 is actually the lower bound on the radius, but actually you can't set the radius to 0 because there would be no way to make a 900 cubic centimeter can with with a base that just vanished into nothingness. And in fact, this formula itself suggests why you can't have R be 0 because you'd have division by 0. So what we know is that actually R has to be greater than 0, which I'll write there. Now, what's the maximum radius? While you're thinking about that, I just want to respond to the person who said the minimum radius is 1. While it is true that the radius can't be 0, the thing you have to realize about real numbers is that there is no lowest real number that's higher than some other number. There actually is a name for number systems where there is a lowest number that's higher than some other number, and those are called well-ordered systems. That's what's called the well-ordering property. That's a few hundred course numbers ahead of where we are, but things like the rational numbers and the real numbers, it's always you can't just say, well, the number that comes after 0 is 1. There's always going to be some fractional or not even fractional in case of real numbers, just some completely abstract number that comes after any other number. There is no lowest number that's less than 0.01 but greater than 0, because you can always just keep subdividing that region. Okay, so anyway, we've now established why all we can say is it's greater than 0, is that R is greater than 0. What about what about the maximum of R? Square root of 900 over pi. So I'm trying to think where that comes from, but no. Yeah, Jennifer's got it right. See, I can always just build like a really, really short but wide cylinder. So let's suppose that this is a radius of, let's say it's, 500,000 miles. I could certainly make the can short enough that, a circle with a 500,000 mile radius, is still going to give me a 900 cubic centimeter can. It's just going to be a very short can. So there's no maximum as to what the radius can be, as long as I'm willing to make the can short enough. So all we can really say about R is that it's less than infinity. So the domain is 0, infinity, and we now have our first optimization problem that does not involve a closed and bounded interval. That makes sense to everyone? Okay, let's hope it does. Okay, so let's that. There we go. Okay, so there's the objective function, and we're going to optimize this. I want to optimize step 4, that on the interval 0 to infinity. So let me give you sort of one way of looking at this. We don't know yet what this function looks like, but what we can do is sort of figure out what its behavior is near 0 and what its behavior is as it goes out to infinity. So recall the way that we examine infinite behavior of a function is we find the limit as x approaches infinity of that function. So, sorry, it's not actually x, it's R approaches infinity of s of R. So this is sort of a review of chapter 2. We are getting close to that time. Don't forget, it's April 6th, and the final exam for this course is May 7th, so 31 days away. God, no reaction to that. And that's okay. So anyway, so 1800 over r plus 2 pi r squared. So, okay. So as r approaches infinity, we're taking a constant and putting it over r, so that's approaching 0. This is just going to get bigger and bigger to infinity, so this limit is equal to positive infinity. I misunderstood that you were stunned speechless by my comment. Yes, that is. Yes, it is going so slowly and so fast. It's like this is a weird month. It's like you really want May 7th to be here because they're predicting that a lot of this problem we're in now will have gone away, but then you have to take a final exam. So it's kind of it's not a difficult choice for me, but I know for many people, I don't know. So anyway, so all right, so what we can see is that as x goes out to infinity, this function is just going to approach positive infinity. So we take limit. Now what we're going to do is we want to investigate what happens as we get close to 0, because we know that's the beginning of the interval we care about. I'm only interested in what happens as I approach 0 from the right, because the function's not even defined, and we're not even considering anything that's happening to the left of 0, because we're looking at the interval 0 infinity. So this is 1800 over r plus 2 pi r squared. Well, by substitution, this part of the function approaches 0, and here we're taking 1800 and putting it over a very, very tiny but positive number, causing this to approach positive infinity. So we can see is that 0 is in fact a vertical asymptote of the function. We can see what this behavior looks like, and then we don't really know what's going on in here, but what's clear is that given that the function is growing to infinity on both sides, the only place that the minimum cost could occur is at one of the critical numbers. So all we have to do is find the critical numbers and determine which one has the smallest value. That's not always going to be the case. That's enabled by the fact that we know that the function grows to infinity on both sides. But in this case, we can clearly say that its minimum value is going to be less than the two infinities, and it's going to have to be at one of these local minima. So we find s prime of r, and that's going to be, just looking up here at what s is, that's going to be negative 1800 over r squared plus 4 pi r. So what we want to do then is set s prime of r equal to 0. Clearly, we don't have to worry about places where s prime is undefined, because the only place where we get an undefined value is at r equals 0, and we've already decided r equals 0 is not part of the domain. So s prime of r equals 0 implies that 4 pi r minus 1800 over r squared equals 0. That implies that 4 pi r equals 1800 over r squared, which implies that 4 pi r cubed equals 1800, or r cubed equals 450 over pi. If you're looking at that last step, all I did is I just divided both sides of the equation by 4 pi. 1800 divided by 4 is 450. So so that means that r is equal to the cube root of 450 over pi. And by the way, that's not plus or minus the cube root. That only applies for even powers when you solve them. So there is only one real number whose cube. There is only one real number whose cube is 450 over pi. So, okay, so that is going to equal that is approximately equal to 5.23. So what that really tells us is that this diagram that I drew really looks more like this. And that at 5.23, it hits a minimum. So that is in fact going to be the value that minimizes that. Remember, this was the surface area function. Surface is a function of r. So recall that h we determined was 900 over pi r squared. So that's going to be 900 over pi times 5.23 squared, which is approximately equal to 10.46. So what we want to do is build a can. Like that. It has these dimensions. So there we go. Kind of unusual numbers, but that's just sort of how it works out. There's the dimensions of the can that has the smallest surface, the smallest possible surface area. I would say that yes, you should know the formula for the volume of a cylinder and the volume and surface area of a cylinder. I mean, especially since I sort of went through the argument as to why these are the formulas for, especially for the surface area. A couple of formulas I would think you should know, or you should know that the volume of a cone is 1/3 pi r squared h. So that's the volume of that cone. Cylinder is a little easier than that. Formula for the surface area of a cone is more complicated. That's really more of a Calc 2 topic. So even though I just force you to memorize it, it's kind of complicated, and I wouldn't ask you to memorize it. So okay. So yeah, you should know the formula for the volume for the volume and surface area of a cylinder. I'm guessing that's RIP to the lack of knowledge of the formula for the volume of a cylinder. That's okay. Oh, by the way, this diagram and the argument that we made here, it kind of demonstrates that even though there is a what is that? There we go. Sorry, pen was doing something strange. Even though there is a point where the surface area is at a minimum, there's no maximum surface area. As you can see, since this is what the surface area function looks like, clearly I can make the surface area as big as I want just by either letting the radius become infinite or, surprisingly, by letting the radius become 0. What you get, at a radius of 0, you get a very, very tall and skinny, or not at 0, but near 0. I should write here, as r approaches 0. you get a very, very tall and skinny can, which is going to have lots of even though it has almost no surface area on the top and bottom, it's going to have lots of surface area on the sides. And if I let R approach infinity, then I get the opposite. I get just a very short and wide can. So even though it has very little surface area on the sides, it's got these huge circles. So there is no maximum amount of surface area for this arrangement. Sorry, I was just waiting for a question. Okay. All right, so let's do the picture frame problem. Oh, sorry, this is a fence problem. It's sometimes phrased as a frame problem, sometimes as a fence problem. So the fence must be, and I promise this is not the same as the pig problem. The fence must be built around a rectangular area of 1,600 square feet. The fence along three sides is to be made of material that costs $120 per foot, and the material for the fourth side costs $40 per foot. Find the dimensions of the rectangle that would be the least expensive to build. So this is not the pig problem. The pig problem gave us a fixed amount of fence and told us to build the largest three-sided fence that we can. This is a little different because the information given in the problem is different. So reading the problem, first of all, what is quantity to be optimized? So what is it? Okay. So Lydia, yes, you corrected yourself. Yes, it is actually dollars. But I asked this because this is something that a lot of people get wrong. They're convinced that if I'm doing a rectangle problem, this has to be about area. I actually haven't heard the perimeter answer yet, but that's the point is that you want to find the least expensive fence. So you want to find the smallest number of dollars that you can spend on this fence. So the way you set this up is sort of like this. I realize I'm using X and Y in kind of their opposite sense, but this is, if this is an X by Y rectangle, then what that means is that the cost of building this side is 120 times X. The cost of building this side is 120 times Y. The cost of building this side is 120 times X. And the cost of building this side, we said the fourth side is going to be a different price, is going to be 40 times Y. So, all right, so what we have to do is write, we have to write cost as a function. So the cost to build this object is going to be 120x plus 120y plus 120x plus 40y. So that equals 240x plus 160y, which is going to be a little bit easier if I write it this way, 80 times 3x plus 2y. Okay. So the only problem is I don't have only a single variable yet, but I should be able to get that from some other information in the problem. This is why it would be completely wrong to say that area is the quantity to be optimized. We're not given any choice as to what the area is. The problem says that we want 1,600 square feet of area. And the question is going to be how we can do it for the smallest amount of money. I mean, the problem is, even pigs have their own protective organizations, and pigs are entitled to a certain amount of area to roam. And we're just the big bad corporation trying to provide the pig with that area for the least amount of money. So, okay. So here we know that since the area is equal to x times y, then that means, and we also know the area is 1600, that means that y is equal to 1600 over x. So kind of similar to how we did this with the can problem, it's just a little bit easier. So, okay, so, we also need the domain. All right, so, sorry, actually, let me just rewrite this in terms of x. So c of x is equal to 80 times 3x plus 2 times 1600 over x. So that equals 80 times 3x plus 3200 over x. There we go. That's the objective function, and we just need to do the domain. So what's the domain of this? Assuming that x is our independent variable, what is the domain of the function? I mean, we do know that x has to be greater than 0. So yeah, so we know x has to be greater than 0 because we can't put a 0 into this equation, but there's no maximum to what x could be, because again, I could always just have a very long but skinny rectangle. So the domain is going to be 0, infinity again. So now for let me just do it here. So for I have cost of x equals 80 3x plus 3200 over x on the interval 0, infinity. C prime of x is going to equal 80 times 3 minus 3200 over x squared. So what I want to do is just look for critical numbers. I know that since 0 is not an issue, I'm not going to get any undefined points in this derivative. So all I want to do is set 80 obviously can never be 0, but the other factor can. So I want 3 minus 3200 over x squared to equal 0. 3 is going to equal 3200 over x squared. That gives us x squared equals 3200 over 3. So x equals, say, approximately equals plus or minus 3266. But of course, I don't really have to worry about the negative because I'm only interested in the interval 0 to infinity. So we'll take that out. And y is equal to 1600 over 3266, which equals 4899. So the pen that we want to build is going to be 3266 for the units feet by 48.99 feet. So the question is, for an exam, would you get easier numbers, or would you just leave your answers in symbolic notation? So the thing about the exam is that it's going to be a lot of questions where you're asked to solve problems and then fill in a blank on Canvas. So for this time only, since we don't really have any way to, normally we have calculator-less exams in person. Since we don't really have any way to control that, what we'll do is, we'll say that you can actually use calculators for this, at least on these types of problems where you would have to, where the main part of the problem is to set it up and know how to solve it. So I'd probably ask for a decimal answer. If this were any other semester, if I gave you a number that came out to a square root, I would just ask you to leave it as a square root. Okay. So, okay. So anyway, so I won't write it in words, but this is the dimension of the rectangle. And if you think about it, this sort of makes sense, because what I have is I have a very long width and a short length, and that's because this side, that side was $40 to build, while the other sides were $120 to build. So it's actually cheaper to build more width than it is to build length. That doesn't mean that you'd think, well, why not just allocate the whole thing to width? But if I had something that was, let's say 0.1 millimeters and 700 miles long, the 700 miles, because I'd have so much perimeter, I'd have to buy so much fencing material with those kinds of dimensions. So what this is doing is it's striking the balance between the fact that the width is cheaper and the fact that you have to have some length to keep the perimeter from getting out of control. So, okay. Any other questions about that? Let's see. Sorry, I'm just looking for a problem that there we go. Apologize for that. Lost one of my slides. Okay. So, sorry, I think there's a question coming. I just wanted to wait for it. Oh, I can just put it up. There's the answer. Okay. Okay, so here's, I don't know why that's so small. There we go. Okay, so this is another type of problem that comes up. I've even seen this on this sort of thing on past final exams. So find two positive real numbers so that the sum of the first number squared and the second number is 48, and their product is a maximum. Like with most, like with most of these problems, it's really a matter of kind of unraveling the word problem. So how would you do this? So the thing to be optimized is the product of two numbers. We'll call them X and Y. So the product is, of course, just equal to X times Y. The problem is that we need to write this in terms of one variable. We want us to create this is the thing, it almost doesn't look like a function, but it is. It seems like a product is not much of a function. But the idea is that it's still an input-output rule. Give it a value of x, it's going to give you a number, which will be the product. So the thing to recognize here is that the sum of the first number and if the first number is squared and the second number is 48. So what that means is that in order to write this in terms of one variable, x squared plus y equals 48, which means that y equals 48 minus x squared. So that means that, let's call it p for product of these two numbers as a function of x, is going to be x times 48 minus x squared, which equals 48x minus x cubed. So now that's the thing that we want to optimize. I guess I want to find the domain. And you have to read that out of the problem. We want two positive real numbers, so we know that x is greater than 0, but there's actually no limit as to what x could be. Now you can make it anything, as long as as 48 minus its square is equal to y. So x is greater than 0, but there's no maximum. So the domain is once again 0, infinity. What we want to do is optimize p of x on 0, infinity. So that's a fairly easy problem to do. We've got p prime of x is equal to 48 minus 3x squared, which equals 3 times 16 minus x squared. That's not going to have any undefined points. It's just going to be 0 when 16 minus x squared is 0. So p prime of x equals 0 implies that x equals 4. In other words, x squared equals 16, so x equals 4, because I'm only looking for positive numbers. So we can then conclude that x equals 4, and we can find y, because y is just going to be 48 minus x squared. Y equals 48 minus 4 squared, which is 32. So the numbers are 4 and 32. Now, by the way, I've kind of skipped over something here, which is I've determined that the only number I have to look at is the one critical number. And I've simply assumed that this is a maximum. So let's say that we want to actually know that it's a maximum. How do we do that? Well, think about what a maximum looks like. Something is a maximum if it's increasing up to the maximum and decreasing downward. Or we might even be able to say that it's a maximum, if this works, if it's sitting on top of a concave down function. So I should be able to validate in either of these ways that the number that I found, x equals 4, is actually a maximum instead of a minimum. This is, of course, what we call the first derivative test. And this is what we call the second derivative test. And they're both saying essentially the same thing. So let's do the first derivative test. All we have to do is pick numbers to the side, to either side of x equals 4. So let's say, sorry, not f prime, p prime of 3. Since p prime is 3 times 16 minus x squared, that's going to be 3 times 16 minus 9, which is 21. And p prime of 5 is going to equal 3 times 16 minus 25, which is negative 27. So we do in fact have increasing to the right and decreasing to the left. For the second derivative test, let's see, p double prime of x, since p prime is 48 minus 3x squared, p double prime is negative 6x. So p double prime, this is why you like the second derivative test. All you have to do is plug in 1 point. I plug in x equals 4, and I see that this is negative 24. What that tells me is that at x equals 4, whatever the function is that gives the product is concave down. So that critical number must be sitting on top of a concave down function and is once again a maximum. So there you go. That's how you know that this is a maximum. Okay. Any questions about that problem? Let me do one more of these. How about this one? I don't want to solve this one all the way through. This one actually comes from Sapling. There's something like this on Sapling. So find the point x0, y0 on the graph of this function, this cubic function, at which the slope of the tangent line has its minimum value. What is the quantity to be minimized? Yeah, it's the slope. Okay. So let's write slope as a function. How do you do that? Correct, f prime of x. So if f of x equals x cubed plus 9x squared minus 3x minus 4, or plus 3x minus 4, then f prime of x is 3x squared plus 18x plus 3. So this is the function to be optimized. Okay. So okay. So the point of this is that this gets a little confusing to say, wait a minute, if I'm going to optimize, I need the derivative. What you would have to do, if I were to go to step 4, the domain, obviously, this function is defined and is going to have a slope on the entire interval, negative infinity to positive infinity. This function this is the thing that has to be optimized. So if I go to if I optimize f prime of x on negative infinity to infinity, what I need to do is find f prime of x prime, which equals f double prime of x, and I set that to 0. And then I go from there. I'm not going to go through the whole process, but that's what you have to do in order to solve this problem. So you have to be a little bit clever about keeping straight the fact that a derivative function itself is a function that can be an objective function. It's the objective function describing the slope. So you optimize it by taking the derivative of the derivative. So that's, I think, what else there is. Okay. Sorry, I'm just waiting for a question. Well, we haven't gotten the value x yet, but yes, when you find that value, okay, so when you find that value x, in other words, the critical number of f prime, which you find by setting f double prime equal to 0, no, you plug that into f prime, because now f prime is the objective function. What you're interested in is what the lowest possible value of the slope is, so you have to plug it into f prime in order to find values of the slope. Okay. Let's see. Okay. What I want to do is I want to shift gears for a minute, because this is now I should point out that some of the sapling problems are a little bit weird. You really just kind of have to ponder them to come up with what the objective function is. Anything that I can tell you about them, we've already done some geometry, we've done some economics, we've done optimization on an open interval, and it's really just a matter of sort of reading the word problem and trying to construct the objective function in the domain, and then you just go from there. So what I want to do actually is give you an introduction to the next topic. This what we've done is now takes us to the end of the material that you're responsible for exam 2, up to section 4.7. Keep in mind that 2 weeks after that, we're going to have the final exam, which will have chapter 5 on it. So what I want to do is start off by giving you a little preview to chapter 5. We're going to go through and cover chapter 5. And then as we get closer to the exam, which is on April 22nd, then I will have at least one lecture that's devoted entirely to review. Exam is going to be primarily on sections 3.2 through 4.7. So we'll go over various topics then a little bit closer to the exam. But now I want to get started on chapter 5. Where is this? So we're going to shift gears a little bit. Up till now, we've been talking largely about rates of change. I said early on, like in the beginning of February, I said the next, something like 7 or 8 weeks of this course are all going to be about slopes of lines and rates of change. And I think I kept my word on that. I think that was pretty much true. So in chapter 5, we introduce really the other half of what calculus is about, and that's area. So imagine that I have a function that looks like this. And it's defined on some interval AB. And what I want to know is what's that area. Now, if this were just a rectangle, I could just say this is the x dimension, which in this case is just equal to b minus a. And then I could say this is y and just say that the area is equal to b minus a times y. The problem is that I can't do that because it's not a rectangle. There's no fixed height of the rectangle. You know, which height would I use? Would I use that height? Would I use that height? Would I use that height? That height? That height? We don't really know, so I can't actually define the area that way. So there are a couple of different ways that we can approach this, but the first one is we do what's called an approximation of the area. So what I would do is, let's say I divide this interval AB into a total of 4 subintervals. And what I do is I say, let's say that I decide that I'm going to draw, let me do these in a different color. Let's say that I'm going to draw rectangles at the end of every one of these subintervals. I'm going to use that endpoint and evaluate the function there. So I draw a rectangle whose height is just the height of the last point in each subinterval. So there's that rectangle. And there's that one. There's that one. And there's that one. So I'm really just adding up all 4 of these rectangles. And that gives, oops, sorry, actually, last one was not correct. There. And that gives like a decent approximation of the that gives a decent approximation of the area under the curve. So what I'm describing here is, this is an approximation of the area under a curve. So here specifically, this is the area under f of x on the interval AB. Am I introducing integrals? I'm not quite at integrals yet. I'm just up to area, which we will find using integrals. So yes, I kind of am getting there. So okay. So the first thing that we're going to do is just use rectangles in this way to approximate the area. The thing that's remarkable here is that it's going to turn out starting in about 2 or 3 sections that there is an amazing connection between the derivative that we've been learning about for the last 7 or 8 weeks and the area under this curve. The way I like to think of it is, you know, if you imagine that up here, you know, there's sort of a mushroom growing out of the ground, and then over here, there's a mushroom growing out of the ground. You know, keep in mind that the mushrooms are really just one little manifestation of a larger creature called a fungus. So there could be like some huge fungus here, where these are actually just different. These are actually just different mushrooms coming out of the same fungus. Basically, at one point, you know, in like 7th grade, you learned about slope of a line. In probably 3rd grade, you learned about area. And what it's going to turn out is that area and slope are actually just part of the same gigantic fungus under the ground, that if you dig deep enough, they're really just different sides of the same coin and the same problem. So that's what we're going to be developing over the next couple of lectures, and that will take us to the end of the course. Okay, so anyway, that's it for the evening. Sorry, I'm a minute over, and I'll see you guys on Wednesday. Thank you. Oh, by the way, don't forget, I will be posting the quiz for this week. It should be around 10:30 tonight, so you'll have 24 hours to do that. 4.4. Is it 4.4? It's I lost track of which section. I think it's actually 4.6. Yeah, it's going to be shape of a graph. Second exam is on the 27th, correct? 22nd, correct? Yeah.